So in this video, I'm not going to solve a problem, but I'm going to try to clarify an issue that comes up for the problems in this section, and perhaps it also came up in the previous semester. It's about this integral to v minus e dot dl, okay? And it's about the direction or the sign of this line element, right? So first of all, let me write this a little bit more clearly. Let's say that I have 2 points in space and I'm going from point A to point B. So this is going to be the potential difference between those 2 points. So that's the final potential minus your initial potential, VB minus VA, is equal to minus this integral from A to B, E dot dl. Okay? So when do we encounter a problem? When do we encounter an ambiguity? Well, try to take this integral. So let's look at the potential due to a single point charge. Okay? Perhaps the simplest problem we can think of. So in this problem, we are going to have some electric field due to this charge. The electric field is going to point every which way, and output from this charge, of course. And I want to calculate the potential. Now, to calculate the potential at any point in space, I need to be given some reference. And let's say that our reference is going to be V at r equals infinity is 0. Okay? This is the usual choice that we make for a point charge. So what I want to do is to start from this point at infinity, and I'm going to just approach some point at distance r. So by taking this integral, since I know the electric field everywhere in space, I should be able to calculate that potential, since I know the value of the potential at the starting point. So one way to approach this is to draw some coordinate system over here with the origin coinciding with the position of the charge, and I'm going to look at the potential at some point on the x-axis, let's say over here, and that point is going to be of distance r from the origin. And I'm going to come from infinity and reach this point. That's my strategy. Okay, so let's do this. So I want to now get something simple over here. So I will try to put the potential at infinity over there. So potential at r minus the potential at infinity is going to be minus from infinity to this point x equals r. So let's call this x equals infinity. E dot dl. Okay. Now you need to take this integral. The way to take this integral is, of course, first to handle the dot product. Now, to handle dot product, you need to decide what's going on. So I can choose any path that I want. So I'm going to start at x equals infinity and come on this point. I will choose to come on the x-axis. Okay. So my path element is just going to be along the x-axis, and my electric field on the x-axis is also along the x-axis. It's purely in radial direction. So electric field is going to look like this. We're here getting bigger and bigger as 1 over x squared on the x-axis. So these are going to be parallel to each other, or are they anti-parallel? Okay. So does this dot product going to be e times dx, or is it going to be minus e times dx? Okay. Now, you might be thinking that because I'm moving in negative x direction, this line element, which is just allowing me to traverse my path, is going to be in the negative x direction, and electric field is in the positive x direction. So this is going to give me a negative sign, but that's not correct. Okay? So this, in fact, becomes minus infinity to r e dx, and that e is given by infinity to r q over 4 pi epsilon naught x squared dx. Okay? And when you proceed this way, this is going to be just 0. The integral of this is just going to be minus 1 over x. So this is minus q over 4 pi epsilon naught minus 1 over x from infinity to r. And if you proceed this way, you're going to get the expression that your v at r is going to be q over 4 pi epsilon naught r. Right? So this minus cancels this minus, and this is going to be 1 over r minus 1 over infinity. 1 over infinity is 0, so you just get this expression, which is the correct expression. Right? So we did not pick up a negative sign while doing this. Why not? So this is what I want to address here. The reason for that is that the L is not the way you traverse your path. It's just a line element. It's a line element in your three-dimensional space. So your dl, so let me erase this, except perhaps just keep the result. Your dl is always going to be something like this. We had, okay? And then this thing over here is going to, so for that example that we were doing, this is just going to go into dx, and this of course becomes e dx. Right? Now, why is this? Why is my dl something like this? Why is it not referring to the path? Now, think about what this corresponds to. Okay? So this corresponds to the potential difference as I go from point A to point B, but this is a dot product. So in fact, this is sum of three products. Okay? The x component of x, E times x component of dl, and so on and so forth. They are multiplied and then summed up. So I can actually do it this way, and I can turn this three-dimensional problem into three one-dimensional problems. Okay, so I can choose in any path as I'm going from A to B, and I will just choose to perhaps just first move in the x direction, and then in the y direction, and then the z direction. I can choose a path like this. Okay, I don't need to move simultaneously in two directions. So if I do that, this really decomposes into three integrals. So the x1 is going to correspond to from ax to bx, dx minus ay dy minus az bz dz. Okay? Now I'm saying that this must be the correct expression. Okay? I'm saying that this corresponds to the correct potential change as I move from the x coordinate of A to x coordinate of B. Right? So if this is correct, then this must be correct for y component, and this must be correct for the z component. And if this is correct, if this is how you go from this to that, then the L must indeed be like this. Okay? So you don't need to worry about its direction. It's always the line element. It's always given by this expression. It's independent of how you traverse the path. It's independent of whether you're coming from some positive x and to negative x, or from some large x to a small x, or from large z to a small z. It doesn't matter. If this is correct, and I'm claiming that this is correct. So let me demonstrate this indeed is the correct expression. I'll just take one of these. So this is now a one-dimensional problem, and I will claim that this is in fact the correct expression for the potential change for motion in one dimension. Right? So what does that correspond to? If I plot this, let's say this is dx, and I'm going to have dx and some positive value for the x component of the electric field. Okay, so this is the simplest case. This is where nobody has any confusion. My x component of my electric field is in the positive x direction, and bx is ahead of ax, so the x component of my final position is ahead of the x component of my initial position. Right? So that integral corresponds to the area under this curve, which is going to be positive. And since I have a negative sign in front of the integral, this is going to correspond to some decrease in potential energy. Is that what we do? Yes, it is. Right? If the electric field is in the positive x direction, and if my final displacement is also in the positive x direction, so if I'm going from some coordinate with the lower x to some coordinate with the higher x, and the electric field is pointing also in the positive x direction, then I'm moving along the electric field, I'm going to have a decrease in my potential. Okay? If you follow the electric field, you'll end up at a lower potential point. Okay, now what if this was not the case? What if this was switched over? What if this was, moving in the negative x direction? As I move from bx to ax, my x coordinate was decreasing. Well, no problem. Then I'm moving this way. I'm moving opposite to the electric field. Okay? And this integral then would not correspond to the area under this curve, but the negative of it. Right? Because the limits of this integral is from ax to bx. And now you're moving, when you're moving from ax to bx, you're moving in negative x direction. That integral is going to be a negative number. With this negative sign, it's going to become positive. And as you move from here to here, you will be moving from a lower potential point to a higher potential point. And you can just play around. You can just say that, what if the electric field was negative? So if it was pointing this way, then it will be a curve somewhere here. Again, it won't just be the area between this curve and the x-axis, it will be negative, that area. Right? You can just play around and convince yourselves that this is indeed the potential difference that corresponds to the motion in the x direction. And by the same token, this is the potential difference that corresponds to the motion in the y direction. This is the potential difference that corresponds to the motion in the z direction. But if this is correct, if this gives the total potential difference, and it does, because I've actually decomposed my motion into 3 different motions: motion in x direction, motion in y direction, and motion in z direction, which I'm allowed to do. So if this is in fact the difference between these two, then the only way that these are equivalent to each other is if the L is always like this, irregardless of the path. Okay, so here, when I showed that this was the correct expression, I checked all the cases. This is indeed the correct expression. And this was independent of the direction of the path, whether I'm starting at a large x and coming to small x, or I'm starting at a small y and going to large y, it doesn't really matter. Okay? This is always correct, which means that this must be the expression. Okay? And if you flip your direction to a to b, but from b to a, then you flip the limits of the integral, which takes care of the sign. You do not introduce an additional sign here. That one, that dl, is always given by this. Okay. Now, this might be a little bit more mathematical detail than you want, and in fact, one pragmatic way to approach this problem is to get an answer and check the answer, verify the answer, right? And you can do this, right? Because in this case, at least, for the point charge problem, this is the potential for the point charge problem, you know what the electric field should look like. And I can take this and calculate the electric field, see if there was a negative sign in front of it or not. Okay, so let's do that. So that potential is going to give me an x component of the electric field, so Ex is going to be minus dV by dx. Okay? And I'm going to write that expression, so d by dx. I need to write this somehow in terms of 4 pi epsilon naught, somehow in terms of x, y, z, so I can actually take the derivative. Right, so this is r in terms of x, y, z. Now you could of course say that this is just x and so on and so forth, but I'm trying to be a bit more complete. So the derivative of this is its derivative times the derivative inside. So the derivative of this expression, it's just the exponent is minus a half. So something with an exponent minus 3/2, and then minus a half comes to the front. So let's write this down. So negative sign coming from here, q over 4 pi epsilon naught. And then the derivative of that introduces minus a half. But the derivative of this is 1 over x squared plus y squared plus z squared to 3/2, and then derivative of this is 2x. Okay? And these go away, these cancel. So if you're on the x-axis, what is going to happen is that your y is equal to 0, your z is equal to 0, so these just drop out. Okay? And x squared to powers 3 halves is going to be x cubed. That cancels one of these. We are going to get q divided by 4 pi epsilon naught x squared. Okay, which is indeed the strength of the x component of the electric field on the x-axis. Okay? This is just going to be something pointing in the positive x direction, which is what you would expect for a positively charged particle. Right? So this is another way. You just start with an expression, you don't care about the sign, and then you check this by using the relationship, the derivative relationship from potential to the electric field. Okay? Presumably you calculated the potential because you knew the electric field. So after getting the potential expression, you can check its sign by checking against the electric field that you already know. Right? But for the mathematical curious, the previous part of this video was the justification for this expression. Okay. Dx ahead, y hat, z k hat. Right?